Now, to close the subject, let's see what is the polar decomposition issue. I told you that this is a very conceptual aspect of a strain that says that in general, in the more general case, the deformation process of any object, of any body, can be decomposed into the composition of first a rigid body motion made of a shifting and a rotation, plus a pure deformation modifying angles and distances. You remember that? So we said that is the polar decomposition. F, which defines the full strain, is the product of a rotation times a stretch, or a stretch times a rotation. Remember that. That's the general case. So the issue is, well, how does this degenerate into something simpler for infinitesimal strain cases? Well, then we can just do operations. How is the expressions of this rotation matrix Q, of these stretch tensors, in the case of infinitesimal strains? That is what is done here. For instance, the stretch tensor, the left stretch tensor, U, that was defined that way. F in turns can be defined as 1 plus J. So this is 1 plus J transpose times 1 plus J. We developed that. Now we apply the fact that the elements of J, the gradient of displacement, are small. So that those terms here are infinitesimals with respect to those. So this applies to that, and that can be just now developed in Taylor series, and finally we obtain that. So finally, at the end of the day, for the infinitesimal strain cases, the stretch tensor can be written as the identity plus the infinitesimal strain tensor. Okay, that's just a formula that can be derived. Essentially, the inverse of the stretch tensor is 1 minus epsilon. Look, what about the rotation tensor? Rotation tensor that was defined in that way, after replacing previous results, blah, 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 blah. We obtain, and that's new, that this rotation tensor can be expressed as the identity tensor plus, that's a new tensor, omega. Omega will be termed the infinitesimal rotation tensor. Word rotation tells something, okay? So, it can be proven that the rotation that appears in the general case can be expressed for the infinitesimal case as the identity plus this. Look, this tensor is defined as 1/2 of J, I recall it's the gradient of the strain of displacement tensor, minus its transpose. So the expression is that. 1/2 of U times nabla minus nabla times U. By the way, in the future, that's something that we will use several times. It's called the skew symmetrical gradient, defined as U plus gamma minus gamma times U. So recall that now we have defined two new notations, so to speak. One that appeared here in the definition of the strains, that was here. The symmetric gradient is U times nabla plus nabla times U. That's the symmetric tensor, and it's called the symmetric gradient of U. Okay, we are divided by 2. That's something that we'll use in the future. And now, that's what defined the infinitesimal strain tensor. And now we have just defined something which just is the antisymmetrical or the skew symmetrical tensor, which is omega. It's U plus nabla minus nabla times U. Look, the component ij is that. And look, this is can be proven very easily that this is a skew symmetrical or antisymmetric tensor. Is one tensor which is plotted here, one tensor that has zero at the diagonal terms, and the terms out of the diagonal mirrored with respect to the diagonal change the sign. Okay? So now we have the concept of a symmetric tensor. Symmetric tensor is just this term is equal to that term is equal to that term is equal to that. That's what a symmetric tensor. And a skew symmetric, antisymmetric, is something, a tensor, which has a zero in the diagonal terms and then the out of diagonal terms are change the sign. Okay? That is the definition of that. And that, of course, by construction, this infinitesimal rotation tensor has the structure of a skew symmetric tensor. And in particular, comes out from the skew symmetric gradient of the displacement. So the gradient of displacements minus its transposed. Okay? So this family of skew symmetric tensors have some interesting properties. We'll look at that. We'll look at what are the interesting properties. The tensor itself is defined in terms of three components. Okay? Three figures. Three figures define a vector, right? Three components we can find in a vector that is made of these three components. That's what we do. So we construct a vector with three components, theta 1, theta 2, theta 3, which is that component minus that one, that component, and that component. By the way, those components from this definition can be written in that way. 1/2 of derivative of u3 with respect to x2 minus derivative of u2 with respect to x3, etc., etc. And then we realize that this is precisely the rotation, the rotation of u, the rotational of u. So we will now write the definition of the rotation of the displacements as we defined at the beginning. You know, the rotation is just the vector product, symbolic product of nabla times u. If we write the components of that, maybe you remember how to do that, no? To write the components of the rotation, what is it? Maybe you have to go back, I don't have it here. But if we look at the components, then we see that this vector is the rotation, 1/2 of the rotational of u. Okay, curl of u, that's the technical word. Curl, C-U-R-L, of u. Okay? So, at the end of the day, what we have found? Well, after all this speech, the tensor that played the role that was responsible for the rotation in the deformation process can be written as 1 plus omega. Omega is a skew symmetric or antisymmetric tensor, which can be defined as the antisymmetric gradient of u, and in turn, from this omega, we can extract a vector, which is called the infinitesimal rotation vector. So look, we have defined omega as the infinitesimal rotation tensor, and theta is the infinitesimal rotation vector, okay? But they are related with each other, because if I know the components of theta, just by replacing them appropriately in there, I can obtain the components of omega, okay? Okay, after that, this omega and theta have an interesting property. That's something that can be applied to any skew symmetric tensor. Any skew symmetric tensor has the following property. If I take any r, okay, any r, any vector, and multiply by a dot product omega times r, what do I obtain? A vector, right? A vector. So whenever I multiply a matrix times a vector, the result is a vector. And now, this vector is exactly the same if I do the vector product of this theta, which is called the axial vector that can be extracted from omega. As I told you, from m omega, I can obtain this vector. This vector in general is called the axial vector extracted from the skew symmetric tensor. Okay? We can always do the same. So if I do that, that equality holds. So what is the interpretation? Now I will prove that. I will prove that now. Okay? But before going to the proof, let me say that this provides an interpretation, a physical interpretation, a geometrical interpretation of that. Look, imagine that I have the tensor omega, a skew symmetric vector, tensor, sorry. From this vector, I can obtain the axial vector extracted from omega, which is a vector, which fulfills that condition for all vectors r. What does that mean? Imagine that I have this vector r, and imagine that the vector theta, the axial vector, is that. How is theta times r, the vector product of two vectors. You know that the vector product of two vectors is orthogonal to the two vectors. So this vector product is orthogonal to theta. Okay? So it stays in a plane which is orthogonal to theta. It stays in this plane. But also is orthogonal to r. Follow me? So I can say that this theta times r will be a vector like that, orthogonal to theta, so it will remain in this plane, it will stay in this plane, and also is orthogonal to r. So it will be something like that, this being orthogonal. Okay? So now, imagine what is the result of summing to r this theta times r, which is, by the way, that remains to be proven yet, omega times r. Okay? Look, that is the sum of that plus that. Okay? So, what happens is this is a very small vector. So if we are now in the case of infinitesimal strains, omega, the components of omega, which are gradients of the displacements, are small by definition. So theta, which in fact are the rotation vector, the axial vector extracted from the skew symmetrical tensor omega, are components of omega, so they are small too. Theta is small, infinitesimal, so to speak. Okay? So this vector here is much smaller than r, is smaller, but orthogonal. That property, which is general for any skew symmetric tensor and the corresponding axial vector, when it's applied to a tensor which is the infinitesimal rotation tensor, then applying theta times r or omega theta times r or omega times r, summing up to r, the result is that is a rotation, infinitesimal rotation. That is why this vector omega is called the infinitesimal rotation tensor. And this vector theta, which is the axial vector extracted from it, is termed infinitesimal rotation vector. Why? Because if we apply to a body, any body, and the vector of position of a particle of this body with respect to a certain point is r, the result of applying r plus theta r would be an infinitesimal rotation of the body. Follow the name? That's the motivation of this name. By the way, it remains to be proven, that equation here, that can be proven just by doing it. So if I take omega, which has this expression, from that I take theta, which has this expression, and then I compute theta times r. R is a vector of three components, r1, r2, r3. Okay? If I apply theta times r, I obtain this expression. If I compute omega dot r, I obtain these expressions. These expressions are the same. Okay? Can be, just it's a matter of checking it. It's checking it. So that's the proof of the theorem that I just stated before. So summarizing, what did I say? What I said is that for the infinitesimal strain case, the rotation counterpart of the deformation can be expressed as 1, the identity, plus omega. Omega refers, or it's referred to as infinitesimal rotation tensor, which is a skew symmetric tensor from which an axial vector can be obtained. This axial vector turns out to be 1/2 of the rotation of u, rotational of u, and the curl of u, and it turns out that these then can be interpreted as infinitesimal rotation. Okay? So, going back to the essence of the polar decomposition, then the gradient of deformation tensor can be expressed as the sum of 1 plus the symmetric part of J plus the skew symmetric plus of J, which is epsilon, and this is omega, so this equation holds. Now for infinitesimal strains, the gradient of deformation tensor can be written as the identity plus epsilon, the infinitesimal strain tensor, plus omega, the infinitesimal strain rotation, And then the fundamental equation of motion that says how a relative position of two vectors at the reference configuration is transformed into a relative position of two particles at the present configuration can be written into this part, 1 plus epsilon plus omega multiplied by differential of x. And then this can be devoted in two parts. That result, epsilon differential of x, and that results 1 plus omega times differential of x. Now we can interpret what is the result of this. So initially we have two particles at the reference configuration, whose relative position is differential of capital X. And what is the final position, relative position of these two particles? Differential of small x. In between, what has happened? That these and these are related in that. First, that particle, differential of x, has been multiplied plus 1 plus omega. Now, since omega is an infinitesimal rotation tensor, this can be interpreted as infinitesimal rotation. So the original vector has been rotated to that being perpendicular. That is the result of the first part. And then the second part says that I have added to that result some epsilon differential of x, which involves no longer now rotations, so change of angles, but most probably also changes of distances. So finally, the interpretation of the polar decomposition for infinitesimal strains can be done in the following terms. Any variation, any deformation involving variations of angles and distances of particles in infinitesimal strain context can be interpreted as the sum, sum, because there is a sum here. It's not a composition, which is the general case. It's just a sum, okay? Sum of what? This term here, which is an infinitesimal rotation, that means that this rotation in the infinitesimal context only changes angles, but it doesn't change distances, okay? Plus a stretch which is defined by the infinitesimal strain tensor epsilon. In other words, in this expression, epsilon produces changes of distances and angles too, okay? But this term, 1 plus omega, is responsible only for small rotations, infinitesimal rotations, which involves no changes of distances, okay? So this is a simplified interpretation of the typical polar decomposition. The polar decomposition that in the general case is thought as a composition. So first we apply a rotation, and on the result we apply a stretch, or first we apply a stretch and on the result we apply a rotation. Now it's just simplified to something which is sum of something, okay? Sum of a stretch plus a rotation, and that's it. How is this defined? The rotation is defined in terms of the rotation, infinitesimal rotation tensor, and the stretches are defined in terms of the infinitesimal strain tensor. Okay, finally, volumetric deformation. You remember that we defined the volumetric deformation as determinant of f minus 1. What is the expression of that in the case of infinitesimal strain? In infinitesimal strains, the volumetric deformation can be expressed as the trace of the infinitesimal strain tensor. The trace, the sum of epsilon xx plus epsilon 1y plus epsilon zz. So, how will we identify in an incompressible solid in infinitesimal strain theory? Checking the trace of the infinitesimal strains. If the infinitesimal strains have tensor, has always a trace which is 0, then the volumetric strain that is the increment of volume per unit of volume, will be 0, so the body won't change its volume. Okay? Of course, this is a general expression. This is just how this general expression turns out to be after that we apply the hypothesis of small strains or infinitesimal strains theory.